Okay, welcome everyone to our very special Patreon seminar. So if you're not watching this live, which likely you aren't, just by the sheer force of probability, and you want to watch this live in the future, you can join the Patreon at the $5 and up tier. It really helps us provide content like this, as well as some other interesting things that I think we're gonna help spread math even further in the future. So today's speaker is Bo Chin. He's from the Department of Physics at the University of Central Florida, and he's going to give us a little bit of a historical interpretation and some background for the 2022 Nobel Prize in Physics. And so I'll give it over to you.
Okay, thank you for the introduction, Mike. It's really a pleasure. So you guys can see my PowerPoint. Just want to confirm. Okay. So today we can review why it is very interesting to talk about this year's Nobel Prize in Physics. So we know already the Nobel Prize this year in physics was given to three fellows, Alan Aspect, John Clauser, and Zeilinger, about their contribution in quantum information or quantum entanglement. So what are the phenomena? So to understand this phenomenon, we need to...
Yes. Perfect.
Oh, all right.
Okay.
Okay, so...
take it away again, thanks.
Sure. If you have a question, feel free to ask. It's okay. We do not have to be formal. I tried this presentation with my students and my colleagues in my department already, so they seems to be quite fascinated. Me too. I heard this talk online given by a Chinese high school physics teacher first, and then I revised it, and here's the version. So to understand the phenomenon, we have to turn back time about 100 years. So that's the famous Stern-Gerlach experiment. So this experiment was conceptually proposed by Stern in 1921, and then was performed by Gerlach a year later. So what happened is you can send a group of atoms, so they send silver, through a gradient magnetic field. So they created by two poles of magnets. And then after gradient, if you learned a little bit of physics 2, or watch some online interesting video, you know that if a material has a magnetic moment and they run through gradient field, they should be deflected. However, the results of the experiment was not as expected. So if things were expected, what they would see that indeed the atom would be deflected, and they would see they strike on the screen along a continuous line as shown by this blue shade area. Instead, what they observed was they saw two distinct dots. So this raised the question. It seems that the magnetic moment of the particle were not continuous. That was really strange. It was anti-intuitive because any physical phenomenon at that time, such as displacement, length, or strength of the force, as we would expect, would be continuous variable parameter. But what we see, this magnetic moment of the atoms are actually discrete value, quantized. So that amazed everyone. In addition, if they tilt the direction of N and S, the poles of the magnetic field, so they can change the gradient direction, they would see these two dots that signifies the magnetic moment direction also realign with respect to the gradient direction. This is even more intriguing. It seems that the magnetic moment's direction also changes with how the way you measure it. That is just absurd. So people start to wonder what actually happened. Is there something wrong with our experiments, or there's something wrong with the classical theory? Okay, so that's the first experiment, opened the eyes of everyone. And we can also check something similar on different elementary particle, in this case, photon, right? Well, in classical physics, the photons, when they propagate along the direction of the green arrow, you can see they have their polarization in the perpendicular plane in a continuous varying fashion. And we can measure this polarization if we pose a polarizer, which has a direction lined up along the polarizer. And only the light that aligns with the polarization, aligns with the direction of polarizer, will be able to transmit after the polarizer. And then you can see the direction of the polarization of the light. So you have a random polarized light initially before the polarizer, and afterwards the intensity will reduce to 1/2. If you perform a integration, you can easily understand this is essentially a projection of polarization of the light along the direction of the polarizer, which is a dot product, as mathematicians would say. And then you have a cosine factor. You would perform average over the angle from 0 to 2 pi, and you get 1/2 factor. Well, this is perfectly fine with classical physics point of view. However, we now know that the light consists of discrete photons, right? So what would happen if we reduce the intensity of a light to such a degree that every single time you only send out one single photon towards the polarizer? It is perfectly fine if that photon happens to have the polarization direction aligned with the polarizer. It will be admitted and pass 100%. If it's 90 degrees with respect to the polarizer, the photon will not be able to pass. It will be blocked 100%. However, if you have a photon that has a polarization direction not perfectly aligned with the direction of the polarizer and not perfectly perpendicular to the direction, you have a difficult situation. And what you will observe is this photon sometimes can transmit and sometimes will be blocked. So it seems it's uncertain, or there's some hidden variable that we do not know about. And this phenomenon, of course, cannot be understood with the classical physics. And now let's take a moment, just backstep a little bit, revisit a ancient or classical experiment called Young's double-slit experiment. So this experiment was originally performed by the famous physicist Thomas Young. Thomas Young is more than just a physicist. He's a man of many talents. For example, he's the one who made breakthrough to decipher the Egyptian character, the ancient character. And he also made the seminal contribution to other fields like vision optics and even music. So the original Young's double-slit experiment was performed with light, where you have a block screen with two slits. And on one side of the screen, you would send out light. And if these two slits are small and they're close by, what you will observe after the screen is after the double slit is on the other side of this double slit, you have a screen, and you will see the interference pattern. So it seems that this demonstrates the nature of the light is wave-like, which is contradicting what we just said about this light passing the polarizer experiment, which something like a particle nature. So this essentially is a particle wave duality of the light demonstration. And then this experiment was reenacted by Davison and Germer in 1927. Instead of light, they use electrons. So they send out electrons towards this double slit. And curiously enough, that we know that electrons are particles. We would expect if things are classical physics-like, after the two slits, you would see discrete band of the electrons on the screen. However, what we actually observed was, again, interference pattern, the band of interference. So what does this mean? This means that in order to generate this interference pattern, the electrons cannot be particle-like, right? If they were particle-like, it has to be able to pass either one of the slit. And if that's the case, they would only be able to generate discrete band after the slit. In order to generate the interference pattern, an electron has to be able to coexist with the possibility to pass through both of the slit at the same time. That's the only possible way for electrons to generate the interference pattern. So this demonstrates that in addition to light, other elementary particles also possess this kind of particle and wave duality nature. And this nature is actually more interesting than this. This was described in 1965 by the famous physicist Richard Feynman in his seminal lecture, Which Way Experiment. In brief, what he described was, he said, I have to admit that I do not understand quantum mechanics at all. And he demonstrated this Young's double-slit experiment as a proof. You will be able to observe this interference pattern with electrons or even other elementary particles as large as a single molecule, which would be a little bit more challenging to demonstrate. However, if you send out the electrons or even photons towards the double slit, and if you try to detect which slit the electron or the other elementary particle or photon is going through, you put a detector behind that double slit, so you can see which way exactly an electron goes through. What will happen is you will see this interference pattern vanishes. This is just mysterious, right? Beyond the intuition for us to understand. It's just like every time we go to lottery to buy a lottery ticket, before we scratch it off, we know, we're sure we are going to have a chance to win. But every time when we scratch it off, there it goes. You're never the winner. So it's beyond the possibility for us to understand. Okay, so now we set a stage to introduce entanglement, the concept. So the quantum entanglement concept was actually first introduced by the famous Erwin Schrödinger. Schrödinger's equation, the base of quantum mechanics. And then the phenomenon of entanglement was first demonstrated by the Chinese physicist, female physicist, Wu Jianxiong. She also made other significant contribution in addition to this. She proved experimentally the violation of parity conservation, which led to the Nobel Prize. And she was not given the Nobel Prize, but she should have. I think it's partly because she was a female. So what she demonstrated was, if you have a positron and an electron, they encounter, and this is called an annihilation experiment. So the positron is everything the same as an electron, except it carries a positive charge instead of a negative charge. So when they encounter, they will annihilate and produce two photons, send their own way. And these two photons are entangled. Their spin states are exactly the opposite. So if one photon is spin up and the other one will be spin down, and likewise the other way. And this entanglement experiment also was borrowed by the other physicist, John Wheeler, to propose a delayed eraser experiments, which we will talk about slightly later. So the concept of this entanglement is just like you have a pair of shoes, and then somehow you lost one of it, and look at the one that you still have at your bedroom. If it's a right shoe, you must know the lost one should be the left. If it's the one in your bedroom is the left, then you must know the other one is the right. You don't have to go find the lost one. So that's basically the entanglement demonstrated by annihilation of electron and positron, giving rise to entangled photon. And then slightly later, David Bohm, the other famous physicist, demonstrated that entanglement is not a unique phenomenon to photons or positrons and electrons. He used the neutral pion to demonstrate you can also generate other entangled elementary particles. In this case, the neutral pion, when it decays, it will send off two particles. One is positron and one is electron. And they also have entangled correlated spin state, oppositely correlated. David Bohm actually is also a very, very unique character in physics. So in his time, he was initially an assistant professor at Princeton. And his advisor is the famous Oppenheimer, in the Manhattan Project leader. During that time, it happened to be the infamous McCarthy era. And David Bohm was summoned to Congress to testify against his advisor, to say that Oppenheimer is a communist. David refused to testify and cited the Fifth Amendment. And because of his activity, Princeton University refused to renew contract with him, and he has to leave his job. But that was not the end of his career. He then went to Brazil and then Israel, and afterwards he set up his lab in England, where he also made a famous discovery with his student, the AB phenomenon, where you have an elementary particle. It can sense the vector field of magnetic field, even though if there is no magnetic field, the magnetic field is zero, but the vector field is non-zero, you will see the change of interference pattern. So that's the famous AB phenomenon. Okay, so let's get back to our discussion about entanglement. So we mentioned that John Wheeler, he borrowed the idea of entanglement and coupled with the double-slit experiment and proposed a delayed choice experiment, which later was repeated many, many times. And this is one of the examples. So what happened is if you send out photon generated by a laser towards the double slit, and the photon can go either the upper slit or lower slit, and after which it will encounter a spatial crystal, BBO, and that will send out the correlated photons. And that correlated photons can go either way, right? One of it will send to the upper corner towards detector D0, or the photon can be sent towards the lower right, and this is a prism. And when it encounters prism, it will be deflected so that it will differentiate towards two directions. One is towards this BS, beam splitter. And this beam splitter, what it does is it can have a 50% chance to send it reflected towards detector D4, or it can be transmitted and sent to a mirror here. And likewise, a lower photon can do the same thing. It will pass through this lower slit and either go towards the detector D0 or descend towards the deflector and encounter with another beam splitter, either be deflected towards D3 or sent towards the mirror and reflected. And what happened is the setup can satisfy such a criterion that the entangled photon pairs, one of it sent to the detector D0, if we say that is signal photon, and the other one sent downwards towards the prism, we call idle photon. We know that if we do nothing, what will happen is the detector D0 detect the signal photon will help us see the interference pattern as what we would expect according to the traditional double-slit experiments, the wave nature of the elementary particle. However, its entangled pairs, when it is sent towards the way, either go towards D4 or it goes underneath towards D3, if the photon originally came in through the lower slit. The path lengths of these two are different. So you will be able to get knowledge of which slit the original photon came through by the entangled partner detection either at D4 and D3, right? So that gives us the information of which way. If somehow that photon passed through this beam splitter, either this one or this one, and they got reflected by the mirror, these two mirrors, and then encounter another beam splitter, and they will be detected either by D2 or D1, then the path length will be set up such a way that you will have no ability to differentiate if the original photon came from the upper slit or lower slit, because the path lengths are identical for both sides. So the message of the setup is if the photon gets detected by D4 or D3, you will have no knowledge the original photon's path. If photon gets transmitted and detected by D1, D2, we sorry, I think I messed it up. If the photon were detected by D3 and D4, you got the knowledge which way it came from. But if they got detected by D1, D2, that path information is not available. So you can correlate this detection of D1, D2, D3, D4 with D0 and make sure to set up that the detection of the signal photon at D0 happens before the detection of D1 to D4. So this is called a delayed choice. So the weird thing happened is after the detection of the signal at D0, if the idle photon were detected and reveal the path information at D3 and D4, you will see no interference pattern. On the contrary, if the path information was disguised by the detection of the partner at D1 and D2, then you will see the interference pattern. So if you just pause a moment and think about it, it seems to tell us that what happened in the future influence what happened already in the past, right? But I have to say that if I reveal the answer to you that is not true, this experiment does not cause a change of the causality consequence in a historical order. You will only be able to see the interference pattern after the correlated coincidence counter detection at D2, D1 are already received. So before that, you do see the signal at D0, but you will not be able to see the interference pattern. Only after you correlate with the signals at D1 and D2, you will be able to see the interference pattern. Okay. All right. So I think I give you enough materials to puzzle about. So how do we interpret all these strange ghost-like stories, right? That significantly challenge the classical physics. So here came the Niels Bohr. He represents the Copenhagen interpretation of quantum mechanics. So here are the main principles. The first one is the famous uncertainty principle. For elementary particles, the properties, the parameters, observables, whatever you call it, they're correlated. And if they're conjugated, correlated, the parameters of A and D, then their uncertainty cannot be smaller than 1/2 h bar, which h bar is the reduced Planck's constant. And what this means is the correlated properties are in a way that you can say like the Fourier transformation correlation, right? We know the frequency and time are a pair of parameters correlated by Fourier transformation. If you have absolute knowledge of the time, you cannot determine the frequency, and likewise the other way. And in quantum mechanics, another example would be if you know the position of the particle precisely, you will not be able to have the knowledge precisely about its momentum. If you know the momentum precisely, you cannot determine its position precisely. So that's the example of uncertainty principle. To know the system, the knowledge of the system is completely captured by the wave function, described the probabilistic distribution of the system, and usually is written in the Dirac bracket symbol. We use the phi here to represent. And then if we want to know how the system behaves, we must measure the physical observables. And the physical observables are the consequence of collapse of the probabilistic distribution to a defined state with the application of measurements. So this is a long sentence and it's a mouthful. How do we understand this? So let's take one step back again to think about what are measurements in classical physics, classical world. For example, if we want to measure the current of a circuit, what we need to do is we have to put an ampere meter in series with the circuit that we want to define the current. And we measured current, the current displayed, the value would be the same current running through the circuit according to the series principle. The reason that the current is the same as the actual current running in the circuit is because the resistance of this ampere meter is so small that it's negligible. So when you connect it in series with the circuit, it poses negligible disruption of the original resistance. Therefore, according to the series connection, the current in the ampere meter should be the same as the original current in the circuit. And likewise, if we would like to know what's the voltage across the resistor, we would connect the voltmeter in parallel to that resistor on the two sides. And because the resistance of ampere meter is so large, approach infinity, so when you parallel it with the resistor, the combined resistance is nearly the same as original resistance. And because they're in parallel, so the voltage across the voltmeter is exactly the same as the voltage across that resistor without the presence of this voltmeter. So in one word, the measurements, when we wanted to define a physical observable in classical world, will not change the state of original system. Or we can make even simpler example. If I would like to know how much I weigh, I just step onto a scale and look at what the scale reads, and it should not affect my actual weight before and after the measurements. That is not the case in quantum mechanics world. Okay, so in elementary particles microscopic world, we have to describe the state of a system as superposition of many possibilities. Let's say the wave function we represent for a specific measurements is represented in this state function represented by this black circle. And that black circle actually is a superposition of multiple different states that I represent as triangle, square, diamonds, and ellipse. And each of these measurements value has their own probability to show up, like 10% for triangle, 20% for square, 30% for diamonds, and 40% as ellipse. So when we are going to do a measurements to define the parameter for elementary particle in microscopic world, is essentially a projection action. So in this case, let's assume that the state represented by the blue triangle and the green square and the red diamond, they consist of three orthogonal states. So when we would like to define the triangular state, what we do is we receive this wave function and we have to project towards the direction of the orthogonal triangular state. And what will happen is out of 10 measurements, one time we will find it actually give us this triangular shape. And likewise, if we would like to know if the system consists of any possibility in this rectangular states or square states, we have to project it towards that corresponding axis. And out of 10 measurements, you will see 2 times it gives you that value. And likewise, if you like to know if the system consists of any possibility in this diamond state, we have to project it towards its own axis along the direction. And out of 10 times, 3 times you will see that value. If we are measuring this triangular state first, and we do see the measurement value, and then if we would like to follow up with the measurements of any possible square states or diamond states, you need to make a projection towards that direction. However, what you will find is every single time you will see nothing after it confirmed the measurements in the triangular state. So what this means is once you made measurements, you irreversibly change the original state given by the system, right? So once you project it and measure triangular state, your current state of the system is no longer this black circle state, but updated as the triangular state. And likewise, if you measured the rectangle state or cubic state, you already updated your system in this green state. Or if you measure first with a diamond state, now the system state will be updated by this state instead of original circular state that consists of multiple possibilities. If in some case you measure first the triangular state first, and then you would like to know what's the possibility to see it in an ellipse state that is not orthogonal to the triangular state, again, you have to follow up with this projection measurements towards the direction of the elliptical state. And because they're not orthogonal to one another, they have an angle between, then what you will see that the possibility to see this state subsequent to the triangular state measurements is the 10% of original possibility times the square of the cosine angle between these two states. So please remember this cosine factor. That's the new possibility after the initial measurements. And likewise, you're not going to see this every single time. So the possibility to not see the system in this elliptical state after the initial confirmation of the triangular state is 1 minus cosine squared, right? So that's easy to follow up. So this is a hand-waving way to show what are the measurements in quantum mechanics world. There is one special case that after the measurements, the system state will not be changed, and that is the original state consists of 100% the state of the measurements that you are performing. So you will not change the state, but that really doesn't change the fact of this puzzling measurements. So we can also introduce a little bit more rigorous treatment with a little bit math. So the measurements in quantum mechanics world can be described by linear algebra, where the state of system are represented by this bracket representation. So measurements corresponding to a projection action to measure the measurements value of its eigenvalue. So if we say A represent operator of the measurements, then when you perform the measurements on some state, if that state is its eigenfunction, it will not change the state of the system and produce the measured value of that measurements. Then we can represent the action of measurements by choosing this eigenstate of the measurements as basis. Then the measurements operator is actually a diagonal matrix in this basis, with the elements across the diagonal direction are the eigenvalues of the measurements. If we say this measurements is to detect the spins, then you can detect the eigenvalue of spin 1/2, spin -1/2, or if it's spin larger than spin 1/2, say spin 5/2, you're able to see the possible eigenvalues from positive 5/2 and then positive 3 halves, and then 1/2 and -1/2, and all the way down to -5/2, lined up along the matrix diagonal direction. And then we can also say that if you choose the basis such that eigenbases are also normal, they satisfy this also normal direction condition, then you can, once you select this eigenstates of the measurements, any other given state of the system can be represented by the linear combination in this basis with the coefficients as the probability amplitude. And this probability amplitude are not necessarily real number, they're complex numbers. And the action of measurements, if we repeat n times, can be represented by this expectation value that's sandwiched by the state wave function phi on both sides, sandwich this action of measurements. And we can plug in the expression. So we know that expression of the measurements are the diagonal matrix in the spaces. So we can plug that in. And then we can plug in the expansion of the wave function of the system on the left side as complex conjugate in these spaces. On the right side as the original expansion as well with their coefficients Cj and Ck. The index are not necessarily the same. Then we can cite this orthonormal condition of the basis and pull out the complex numbers to the front as well as the eigenvalues of the measurements to the front, right? And then we left with the dot product of the basis between I and j and I and k, which will give us delta function that help us to reduce the summation over ijk to a single summation of I, where the AI again represent the eigenvalue of the measurements, and Ci and Ci complex conjugate multiplied together represent the possibility or probability to obtain that specific measurement value out of n measurements. So that's the quantum mechanic rigorous treatment of the measurements. And let's map this measurements theory to experiments. Again, let's send the unpolarized light towards the polarizer. And after polarizer, the direction of the light, the photons, will line up with the polarizer. So we can say that original wave function is the superposition of all the possible eigenstate where alpha I and all the way to alpha n represent the polarization eigenstates. And C1 to Cn represent the probability amplitude. Well, I have to say that rigorously, this is not true because I'm written everything as a pure state. In reality, the unpolarized light is a mixed state, but let's make things simple to say that this is a simplified view of what is happening. So what will happen is after the first polarizer, if we say the first polarizer is to measure the eigenstate of alpha 1 with the eigenvalue of A1, when it acts upon this unpolarized wave function phi naught, and this is the representation in mass, the theory we just introduced. And then this, we can plug in the expression of phi naught, which will have this projection of alpha 1 interact as a dot product with all the possibilities. And according to the orthonormal condition, then it will leave us with the only possible eigenstate of alpha 1. And the new state is updated as the alpha 1 state with the possibility of the C1 in this case. And after that, if we follow up with a second polarizer, then you have to repeat these measurements again on the new state function phi 1 that represented here. And that measurements will have its own eigenfunction A1 along its eigenstate alpha 1 that interact with the new wave function. And we can insert the wave function phi 1, which is the C1 times alpha 1, the eigenstate after the first polarizer. And we can put to the front the number, the numerical numbers. And then you have the dot product between the measurements of alpha 1 state with previous surviving state of alpha 1. So what will happen now is this dot product will produce a cosine factor that signifies the direction difference between the second polarizer's direction with respect to the first polarizer. And that's the possibility you see the light or the photon to pass after the second polarizer. And if this angle is 90 degrees, you will see the photon will be completely blocked. If the angle is not 90 degrees, you will see sometimes it is blocked, sometimes it is not blocked. And if you measure n times, the possibility to transmit is described by this cosine square phi. And the possibility for it not to be able to pass or it to be blocked is 1 minus cosine square phi. Okay, so let's remember this cosine square phi factor that represent the possibility to be the system in the state of the second polarizer, and 1 minus cosine square phi represent the possibility of the system to not in the eigenstate of a second polarizer. We will cite this conclusion in a subsequent Bell inequality proof. So now we're able to understand the most of experiments that we just introduced at the beginning of our talk. But you may ask, how do we understand the quantum entanglement phenomenon, right? We did something to the idle photon, but somehow affect at a distance the signal photon, the pair partner of the entangled photons. So according to Copenhagen's view, this is in the mythology the same thing as co-joint twins for entangled particles. Anything that you do towards one of the twin, the other one will feel it, no matter where they are. It seems to be absurd, right? It's anti-intuitive. Not only we, but famous physicists, probably the most famous physicist without introduction needed, Albert Einstein, he felt infuriated. So he started to look for flaws, and it's very easy to find. He said that this is absurd. Everything that we know up to today in physics is purely deterministic. And the famous saying, quote, is God does not play dice. And if Einstein were alive, I guess he must say that even if God played dice, he must have knowledge of every parameter, like the direction, how he throws the dice, and the strength applied on the dice. So he knows the initial velocity of the dice completely well, and he knows the material of the dice as well as the media where the dice is going through, and the final landing towards which he's going to interact. Then the God must be able to predict how the dice will land and what's the number will show up. And he also says that the moon should always be there, even when we cannot see it. And this is probably targeted towards the puzzling double-slit experiment. If you pick at it, it will disappear, the interference pattern. If you don't pick, it will give you the interference pattern. And this obviously does not agree with the moon. Even we don't look at it, the moon should still be there. And we look at it, of course, it is there. And the most unacceptable thing in Einstein's eyes, if I were alive at the time, I would side with Einstein, is the contradiction to the locality. I believe in his eyes, this is a heretic view, right? The quantum entanglement obviously contradict the locality of the classical physics. And it is high crime on his list. So Einstein thinks quantum mechanics is an incomplete theory, and there must be a hidden variable that we do not know to solve the mystery of uncertainty and other things. So how do we understand the puzzling behavior? For example, the photon sometimes can pass a polarizer, and the same photon in other occasions refuse to go through. So this can be explained in the view of Einstein and others there must be some hidden variable that we do not know, we have no knowledge. And that photon can be labeled by some hidden variable. And this hidden variable in this case is yellow. And likewise, that identical photon in our eyes without knowledge of that hidden variable can be also labeled blue, which we cannot see, and can be labeled by a third color, red, as well. So sometimes we know that photon can pass if it's labeled red, but that same kind of photon can sometimes simultaneously be labeled by blue. Then that photon will not be able to pass. And if its photon is labeled by blue completely, that photon will be able to pass every single time. And likewise, you can have other possible hidden variables label the photon that we have no knowledge of. And you can label it simultaneously by 3 different hidden variables. So Einstein proposed, contrary to Copenhagen's quantum mechanics view, our science and technology is not sufficiently advanced. So we do not have that knowledge of hidden variable. And then in our eyes, what we see are this puzzling behavior of uncertainty or probabilistic behavior of the elementary particles. And then give us the puzzling behavior of entanglement, as well as the peekaboo activity of the double-slit experiments. And he also proposed conceptual experiments to ridicule Copenhagen's quantum mechanics view. And this is the so-called famous EPR paradox with his friends, Podolsky and Rosen. So this experiment goes like this, at least one version goes like this. In the source where you can generate an entangled pair of photons, and you would send one of the photons to Alice and the other one to Bob. And Alice and Bob are at millions of light years away at different galaxies. So there's no way they can communicate with each other simultaneously. However, we can schedule a GPS device such that Alice and Bob will perform 2 experiments on their ends simultaneously. What Alice will do is Alice will characterize the position of the photon. And at the same time, at millions of light years away, Bob will perform measurements to characterize the entangled pair of the photon that he possesses, the momentum. So there is no reason either Alice or Bob cannot define the position of the photon or the momentum of the photon in their position at a time. Correct? Because any possible communication between the entangled pairs in their position will not be able to transmit through light years away distance simultaneously, instantaneously. If that were true, the conclusion that obtained precision measurements of the position and momentum at the same time will violate one of the pillarstone of Copenhagen's quantum mechanics, which is the uncertainty principle, where you should not be able to define the conjugated parameters at the same time, which position and momentum happen to be one pair of such. So obviously, this cannot be true. So you must either violate the principle of uncertainty or the entanglement is not true. So we're facing this dilemma, right? There's no way for us to send Alice and Bob to somewhere light years away. To my best knowledge, the furthest satellite human-made sent out is just past our solar system, the Voyager 1, a few years ago, if I remember correctly. So there's no way this experiment can be performed to prove what will happen. And either Einstein or Niels Bohr, both are giant in physics. So they have their own authority. It seems that there was no way to settle this duel of their contradicting belief. And it's very difficult to see how to solve it, how to find out which one is true, because both proposals are effectively the same to be able to explain what we can observe. Well, here comes our famous John Bell, the Irish physicist. John Bell actually is not trained in this quantum mechanics view. His job is doing theoretical calculation regarding accelerator, and one of his famous contribution is how to set up and tune the focus of the accelerator, the magnets, to focus the elementary particle beams. But I think his most famous contribution is the Bell equality. There are many versions of this Bell equality, but I think this is the most intuitive way to show that how elegant a method this is to solve that look like impossible duel between two giants. So here is what Bell proposed. If we have a elementary particle and one of the physical observable can have three different states, we represent them as A or B or C. If these states' properties are deterministic, even though it can be determined by some hidden variable, then what they must satisfy is this inequality. The possibility for the system to exist in A state, but not B state, is represented by this circle with the blue and red, plus the possibility of the state exists in B, but not C, which is this area. If you add these two, this Venn diagram should have larger area than the system to exist in A, but not C. So this is obvious. It's intuitively obvious. This must be true. If the system is determined by uncertainty probabilistic distribution as proposed by quantum mechanics, then this relationship will be violated. The secret of the success of this Bell inequality is John Bell was able to go beyond the yes or no relationship, or the photon that pass or either pass or block by a polarizer that line or 90 degree with respect to it. He was able to account for the non-orthogonal possibility, which is the cosine factor inherent to the quantum mechanic distribution of the state. And we can set up such a, okay. So we can set up such a measurements of three different states of a system by entangled photon pairs. So we would send one photon towards polarizer one, and then its entangled pair towards the photon polarizer two. They have the same state wave function. Let's ignore the spin state are possibly anti-correlated. Let's say they're always the same to simplify the description. So what we can do is we can set polarizer one to align with a direction where polarizer two to be either aligned or 90 degrees with respect to the polarizer one's direction. So what will happen is, if we send polarizer 1 a line along the vertical direction where polarizer 2 is also aligned along that direction, we're measuring the system in the A state and A state. So you will see 1 if you measure the coincidence of this. So the photon will be able to pass 1, and the other entangled pair will also pass 1. If the photon 1 is not able to pass 1, and this second one will not pass the second one as well. And likewise, if you set the polarizer 1 to be horizontal direction, you set that polarizer 2 also in horizontal direction, which is orthogonal to the photon's polarization direction. What you will see is the photon 1 cannot pass 1, and the photon 2 cannot pass 2. So you measure the A naught and A naught possibility. And also you can perform a conjugate measurements where you set photon polarizer 1 to be orthogonal to the direction of the entangled pair, while the other polarizer set to be aligned with the polarizer's direction. Then you will see this one cannot pass, and this one will be able to pass. So you measure 0 in the coincidence counter. And you can switch the direction and you get the same result. And then we can introduce 2 other different states where the B state will be aligned a theta angle with respect to the original entangled pair's polarization direction. So then if you set the polarizer 1 align with the entangled pair's polarization, photon 2 will go under the polarizer at a cosine angle with respect to its polarization. Then the coincidence counter to measure the possibility of polarization, polarizer 1 set at this angle and polarizer 2 set at the cosine angle to see the possibility that photon 1 pass and photon 2 not able to pass is described by this 1 minus cosine square as we introduced earlier, right? So so that's 1 minus cosine square factor. And then you can set up the polarizer 1 as the B state, which is theta angle with respect to A state. And then polarizer 2, you set up at 2 theta with respect to the entangled pair's polarization. But that state C is only making theta angle with respect to B state. And this will help us characterize the possibility for photon 1 to pass the polarizer 1, but photon 2 to be blocked by polarizer 2. And that possibility, when you count the coincidence rate, will give us 1 minus cosine squared theta factor, because the angle between these 2 states is theta factor. And then we can also characterize what's the possibility for the entangled pair to pass the original state that align with the polarization, and the third state C with 2 theta angle with respect to its polarization. And that possibility to be blocked by the third state is 1 minus cosine 2 theta factor. So these 3 results corresponds to the 3 scenarios described in Bell's inequality. And we can look at them using simple middle school trigonometry if they satisfy the Bell's inequality. So what we have on the left-hand side are 2 times 1 minus cosine square factor to describe a system in A state but not in B state, plus the possibility of the system in B state but not in the C state. On the right-hand side, the possibility according to quantum mechanics to in A state but not in C state is described by 1 minus cosine squared 2 theta. So you can easily see that left-hand side is equal to 2 times the sine square factor, where the right-hand side is sine squared 2 theta. And we can expand them using the double angle formula on the right-hand side. So you open up with 2 sine theta and cosine theta and overall square. And then we can compare the ratio, left versus right is a sine versus 2 sine theta. And that gives us a tangent angle less than 2 will cause us to violate this Bell inequality, which means if we set angle less than this arctangent 2, which is 63.4 degrees, we should expect the violation of Bell inequality. Is that true? That's what the Nobel Prize this year, the 3 winners, they proved. So the first proof was given by Joan Clauser. You may wonder why the female Chinese physicist didn't prove it, because she already discovered the entangled quantum. Because that annihilation experiments, the efficiency to generate entangled pairs of photons were terribly low. So she was not able to apply that experiment to confirm Bell's inequality. On the other hand, John Clauser, he used different material, different experiments. He cast ultraviolet light on the calcium material, which would excite calcium to the excited state. And after excitation, it will go back to the ground state and send out correlated entangled photons, which has much higher efficiency. And that's what he used as source to generate entangled pairs. And then he would send one of the photon to one side detector and the other one to the other side. And he showed that actually, as quantum mechanics proof, we just showed the Bell inequality was violated, and which showed us probability is the correct interpretation. Copenhagen view is correct, and there is no hidden variable. However, many people were still not convinced, because there's still a possibility of secret communication between the particles, the correlated particles. What if they got the knowledge of the setting of the polarizer before they arrive at the polarizer, and they switch their hidden variables value, so they somehow adopt the value that consistent with the Copenhagen interpretation. So to prove that is not the case, Alan Einstein, he came up with his own design of the same experiments, where he introduced a setup to separate the polarizer by a good distance of 13 meters. And the fastest thing that we know to travel across this 30 meters is light, and that should take longer than at least 14 nanoseconds. And then he also enabled a random switch of the polarizer's direction between the 3 states at a speed faster than the light speed to transmit between this distance, as short as 10 nanoseconds, which means they will not be able to have the speed to communicate between each other and switch their hidden variable to adjust their polarization direction. So this shows that the heresy believed by Einstein is not correct. So the quantum entanglement actually is not constrained by the Einstein's locality principle. And then in 2008, this experiment was repeated again with the 2 polarizer pull apart to as far as 18 kilometers. And they, again, proved this locality is not obeyed by the entangled photon pairs. So if you do something to one of the entangled particle, no matter how far the other particle is, it will be able to make the adjustment. And that is so-called, they share the same wave function that is not restricted by physical distance. And whatever you do the measurements towards one of the entangled particle, it will cause the collapse of the wave function that reduce the uncertainty to a defined state, not only to the particle that you perform measurements to, but also to the wave function of the entangled particle pair at whatever the far distance that it may be. And what you may wonder what Anton Zeilinger did. There were still people not convinced. What if the entangled quantum pairs, they have some mysterious ways to communicate their knowledge with a speed faster than the speed of light, something that we still have no advanced technology to discover, but nonetheless does not stop movie makers to make different interesting movies like Terminator or Back to Future to challenge how fast things can travel, right? So that's what Anton Zeilinger said to convince people. He first improved the efficiency of detector to further reduce the possible error. And in 2017, experiment was repeated again, where to code the direction of the polarizer to detect the three states, not by random number generator. If you have taken any programming class, you may have the knowledge, the random number generator, any random number generator that is, if you like to use, is not truly random. If you know the seed of the random number generator that you use, then any subsequent so-called random number spewed out by the random number generator can be faithfully predicted. So to take that out of the question, the 2017 cosmetic Bell experiment, they take the cosmic light received by astrophysicists that came from 600 light years away and code the parameters of the light as a seed of random number generator. So there is no way this seed can be acquired, this knowledge, by anyone pre-handed, because the light came 600 light years away. And then in 2018, the Big Bell test was conducted to further eliminate the human being factor from this previous experiments, the setting of the random number generator. So what this did was they set up an online website to invite any volunteer globally to click on the website 0 and 1 randomly. So you have no control who will participate and what they will click and what order they will click, 0 and 1. And they use that to code the random number to determine the direction of polarizer. So they selected 100,000 participants globally, and the experiment again confirmed the Bell inequality is true. So I think that put all the conspiracy to the rest. And these three gentlemen were awarded the Nobel Prize because their contribution to the busting of the quantum entanglement. And what lessons we can take away from this? We can say that life is like quantum mechanics. The only thing certain about is uncertainty. And now we know why life is so unpredictable, because all the elementary particles are unpredictable. And we must know that nobody is always right, even the famous Einstein. So we have to keep open-minded, respect the facts, not authority. And that's how science advances. And the truth is always out there. And this world is more interesting than we can imagine. And thank you for your attention.
Thank you. Are there any questions? Yeah.
I hope I'm close enough now. So I wanted to ask, a lot of this was about like the Nobel Prize winners. Can you talk a little bit more about like why it's so important to wait so long to award the Nobel Prize for things like quantum entanglement, and why we can't just do it when these discoveries or like groundbreaking experiments are first performed?
I'm not authority in that aspect. I can only tell you how I understand, which may be wrong. My interpretation is, as you can see, the third experiments by Anton Zeilinger was just finished in 2018, right? So it's pretty close, 2022. And we must know that every year, there are different proposals brought up to the Nobel Prize Committee. There are many different possible candidates. And the Nobel Prize Committee must select from all the proposals to determine which one would be awarded. So this involves a subjective determination who will win. So you may not be selected even though your contribution is deserves it. And there are many cases that the discovery should be deserved a Nobel Prize, was not. And it takes years for the proposed theory or experiments to be recognized, their truth, or recognize their significance. Another example is the famous Einstein. That we know Einstein is probably the most famous, the smartest physicist alive. Not alive, I mean up to date. He won Nobel Prize, but that was not because of his contribution in special relativity or general relativity. Is because his contribution in photon electric effect. You see, when people try to determine what is to be awarded Nobel Prize, sometimes they do not agree with the general public years later that we appreciate probably the significance of general and special relativity is more significant than photon electric effect. This does not mean that photon electric effect is not significant. Isn't in that I think most people would think special relativity or general relativity is more significant. But it was not the case when Einstein was alive at the time. And it takes many years to prove the general relativity is true. And then sometimes people die young and you don't get awarded at all, even though your discovery is deserving a Nobel Prize. For example, John Bell, if he were alive today, I believe he would be at least among the Nobel Prize winner this year. And that means one of the winner has to be replaced by John Bell. So you have to be healthy as well. And many different factors. I hope I answered your question.
You have another one? Yeah. Come on to those so you can be seen on the camera.
Hello.
Hi.
So I had a question about quantum computers because they're supposed to be using entangled particles, but if we can't determine what those are without observing them, how would we ever be able to get predictable results from that?
To be frank, I have little knowledge of quantum computing, so I'm afraid I cannot answer that question. I think this has to do probably with if we're good with math, we sometimes think that everything works just like math, black or white, right? But actually, if you think about things, the decision making of human mind sometimes is not black and white. It's not 0 and 1. And sometimes there's a blurred gray field in between. And then that makes the human intelligence, not able to be fully replicated by the 0 and 1 computation. So maybe that's why quantum computation can help. In this case, there's certainty and uncertainty plays in a role. Before you take the measurements, you do not know what exactly the state of the system is. And that's something like what Schrodinger trying to explain the quantum mechanics using his cat to demonstrate. Before you make the detection, the truth is actually simultaneously existence in both states instead of one defined state. The cat is in an undead and a dead state until you open the door and you see, oh, it's dead or it's alive. So frankly, I am not expert in that field. I cannot really answer that question, why quantum computation can help. My own research field is biophysics, but I'm interested by this year's Nobel Prize, so I just dig a little bit and give this seminar to help more people appreciate how fascinating physics can be. So maybe future you can make quantum computation a reality, then something has to be happen in cold temperature that we cannot really own a quantum computer now.
Thank you.
Hello. Morning.
Hi. Morning.
So this is kind of more of a generalized question and may or may not be already answered, but I was kind of curious to how, I guess, this continued experiment would help society in a way. Like, how did this experiment leading to a Nobel Prize, the recent one, help us out in society? Like, yeah.
Oh, yeah. So if I understand correctly, you mean what's the possible application for quantum entanglement, right?
Yeah.
Yeah. So one immediate thing that people would be latch on is from military. You want communication, secret communication of message not able to be interrupted. And if you were interrupted by your enemy, you must be able to find out your monitor. And that is nearly impossible nowadays. And you watch the movie from Second World War about Enigma, right? Once you intercept the code of the message, then you're able to reveal the content. And that can sway the direction of the war or history. And that will not be the case if you use quantum entanglement to code your message. So first of all, if you code a message by this pair, you leave one message in the headquarters and you send the other entangled pair to your division in the battlefront. And it will not be intercepted. If it were intercepted, to decode the message, they must perform the measurements. And once they perform measurements, it will cause collapse of the quantum state immediately. And then you still have the possession of the other pair in the headquarters. And you keep monitor the pair that you have your possession. If it were intercepted at instance other than the instance where your division's general is going to reveal the message, you know that is not your general listening to you. So you immediately see somebody else then your own people are reading your message. So conceptually, this, at least for what we know now, there's no way for a third person to decode the message that is coded by entangled quantum pair without being discovered. At least at this moment, technology does not allow that. So that means it is a superior form to use quantum entanglement to code a secret message that can be used in different ways, not only military, but also your credit card, for example, that can prevent possible theft online, and everything. You can use this coding mechanism. I think nowadays the coding mechanism is by prime numbers, distribution of those things. So with current advance of mathematical knowledge, people are getting better understanding of the distribution of prime numbers, the gap between prime numbers, for example, is being shrinked. So it seems to be more secure if we use the coding mechanism with quantum entanglement. I hope that answers your question. That's one example. Of.
Any other questions? Hey, I have a question. So I'm not a quantum physicist, so my bad if this is a dumb question. So I'm just a little confused about the time evolution. I mean, when you have something like 40 nanoseconds, it's not a big deal. But if you've prepared your system in a superposition of eigenstates, even after a measurement, right, you may have a time evolution in the probability. So I'm a little confused about that. If you're now going to longer baseline, so how does that affect this, or is it just negligible?
So I guess if I understand correctly, you're wondering that how you can prepare a system with sufficient lifetime to preserve the pure state of the quantum mechanics state. I guess that's why that most of the entangled pairs, they have a short lifetime, and that's why quantum computation has to be performed nowadays at ultra low temperature. So you have for example, the Bose-Einstein condensation state with really long lifetime. And if you raise the temperature, the thermal agitation would introduce noise and the interaction with the particles to reduce their lifetime. Yes, that is a concern, actually. But if you have a entangled pair that created at low temperatures, where the interaction with the environment can be reduced to the maximum, so you can prolong their lifetime. So they have the system in a steady state, even though the steady state still oscillate as a function of time. But according to Schrodinger's equation, that oscillation of the steady state will only acquire a phase factor that does not affect the complex conjugate factor, right? You will phase out, you will cancel the phase factor. So you will get a steady state distribution of defined time independent measurable probability. So, but once you cannot achieve that isolation state of the system, then you will have the situation where the lifetime is so short, you will not be able to preserve it over long enough time, where one particle is sent to one distance and the other one is at far distance away. Yeah, so that is, I think that's one of the technology challenge in this situation. That's why most of the quantum computation are performed at low temperature to try to maximize the lifetime, so you can preserve the entangled state. Otherwise, it wouldn't be there.
Any other questions from anyone? All right. Well, thank you again. This was a great talk.
Thank you.
Thank you.